This is the second video on antiderivatives, so if you haven't watched the first video about what the basics of antiderivatives are, you may want to go back and watch that one first. So in this second one, we're going to be learning how to deal with what I'm going to call sort of baby chain rule, how to take the antiderivative of a composite function when the inside function is linear, and we're also going to be learning about initial conditions, or so-called boundary conditions, and what those mean. So let's start with the baby chain rule. So let's say I want to evaluate something like this. So remember, this integral symbol with the differential means I'm taking the antiderivative. And we know that if I just wanted to do sine, the antiderivative would be negative cosine plus c, right? Because remember, we're doing general antiderivative, so we add the plus c. If I take the derivative of negative cosine, I end up with sine. So that's what I would get here. Now, the issue with this one is, right, I've got this 5x plus 3 on the inside. So it turns out the fix for this isn't too bad. So I am still going to have to think about, if you think about what the chain rule does, I would take the derivative of the outside function and leave the inside alone. So I'm going to sort of take the antiderivative of the outside function and leave the inside alone. So I'll get negative cosine 5x plus 3. Right, and I'm going to have something, and then of course my plus c gets tacked on because we're doing a general antiderivative. The problem is, though, if I take the derivative of this function, right, I'll take the derivative of cosine, which gives me negative sine, so that'll cancel this out, and then I'll have sine 5x plus 3, but then because it's chain rule, I would also multiply by 5 when I take the derivative. But I don't see a 5 here, which means I have to sort of introduce a 1/5. I have to scale by a constant to counteract the effect of the chain rule here. Right, so remember, I'm trying to undo the derivative process when I do this. And so if you can check, I'm going to sort of rewrite this a little bit. So negative 1/5 cosine 5x plus 3 plus c. And you can check that if you take the derivative of this, you will in fact end up with sine 5x plus 3, because again, you take the derivative of cosine and you get negative sine. That cancels your negative and gives you your sine 5x plus 3 because you leave the inside alone. Then when you multiply by the derivative of the inside function, it's a 5, which will cancel this 1/5. So basically, when you have something that's linear on the inside of a composite function, you just have to sort of undo the scaling. So in this case, the scaling, if you were taking the derivative, would be multiplied by 5, so you have to counteract that by doing a multiply by 1/5. So let's see that again. So say I have 1/7 x plus 4 to the 6th, right? I know if I just had x to the 6th, power rule for integrals tells me that that would be 1/7 x to the 7th, right? Plus c. So I know I'm going to get 1/7 1 over 7 times x plus 4 all to the 7th. This is the sort of antiderivative of the outside, leave the inside alone, and I'm going to have my plus c. But then I know that this 1/7, if I were doing the derivative of this, remember, whatever I get on this line, when I take the derivative, I ought to end up with this. So if I take the derivative of this, the 7 comes down and cancels this 1/7, fine. I subtract 1, which will give me my 1/7 x plus 4 to the 6th. But then I'd also have to multiply by the derivative of the inside function, which in this case happens to be a 1/7. So I'm going to have to undo that scaling by multiplying by 7. Now remember, you're going to be multiplying by the reciprocal. Like here, when you did the chain rule, you ended up multiplying by 5. You want to undo that 5, so you multiply by 1/5. You don't double down on it, right? So here, in the chain rule, when I multiply by the derivative of the inside function, I would multiply by a 7th. I need to undo that multiplication by a 7th, so I multiply by 7, right? So in this case, this 7 and this 7th cancel each other out. And you can check if you take the derivative of this, you do in fact get this. Now, this is a sort of weird combination of numbers, right? Because the denominator here is 7 and the exponent ends up being 7, which is why they cancel out. That's not true in general, right? But I just wanted to show you one where the numbers are kind of weird to indicate that that doesn't mean you're doing anything wrong. And you can always check, if you take the derivative of this, you ought to get back at this. Okay, so that's the so-called baby chain rule, which is if you're trying to anti-differentiate a composite function and the interior is linear, then you basically just have to adjust by a constant, where the constant is the reciprocal of whatever the interior function's derivative was. Okay, so now let's talk a little bit about initial conditions, or so-called boundary conditions. So sometimes we have initial conditions or boundary conditions. Those sort of terms are interchangeable for your function, which means that you can solve for a specific antiderivative rather than the general one. So you don't have to have plus c on your answer. You can recover exactly what the constant was. So, for example, initial conditions look like this. F of 0 equals 12, for example. So I know something about my original function. So recover f if f prime is this and you know something about the original. Okay, so first, recover the original function if I have the derivative. So that's asking me to anti-differentiate this, right? So that's the first thing I have to do, because that's going to take me from this back up to the original function. Okay, so f of x is going to be equal to the antiderivative of this. So my constant just gets carried along for the ride. If I anti-differentiate e to the negative 2x, I get e to the negative 2x. And this is baby chain rule, right? So like the interior is a negative 2, which means I'm going to need to multiply by a negative 1/2 to sort of counteract that 2 that would come out. And then plus c. So again, this is our sort of baby chain rule type problem. We know that when I take the derivative of the inside function here, a negative 2 is going to come out, but I don't have that negative 2 here, so I have to sort of cancel it out with a negative 1/2. And you can check that if I took the derivative of this, I would in fact end up over here. So we can clean this up a little bit, right? I mean, negative 1/2 times 10 is really just negative 5 e to the negative 2x plus c. And then now, here's where I'm going to use my initial condition to eliminate plus c. So this is f of x, and I know that when I plug in 0, right, so that's negative 5 e to the negative 2 times 0 plus c, that's supposed to be equal to 12. So in other words, negative 5 times 1, because e to the 0th is 1, just like anything to the 0th is 1, is 12, which means that c is equal to, right, I can add 5 to both sides, c is equal to 17. So my original function, the exact antiderivative, so here's the general antiderivative, but the exact antiderivative is negative 5 e to the negative 2x, and then instead of plus c, I know that in this case c was 17. Okay, so here is the exact antiderivative. So again, the idea with initial conditions is if you have some extra information about the original function, you can recover the exact constant rather than using a general constant of integration. So let's do one more. So by the way, let me introduce this term differential equation. You may have seen that before or heard it before in mathematics and not known what it was. A differential equation is basically recovering an original function from its antiderivative or from its derivative. So in this case, we're going to step it up a notch and do the second derivative and recover all the way up 2 steps and try to recover the original. So solve the differential equation. So d2y dx2, that's Leibniz notation that says the second derivative of y is 12x squared. And I want to know what the original y was. And for every derivative down you need an extra initial condition. So here I've got 2 derivatives down, so if I want to be able to recover the original function, I need 2 initial conditions, so 2 different points to sort of pinpoint what's happening. Okay, so first thing, if I want to go up a single step, then I need to take the antiderivative for this, right? So if this is the second derivative, then the first derivative will be whatever I get from taking this antiderivative. So using power rule for integrals, this will be 1/3 x to the 3, right? Plus, and I'm going to say c1 this time, my first constant, because I'm going to be taking more than one antiderivative. Okay, so I'm going to clean this up a little bit. 12 times a third, that's 4x cubed plus c1. Right, and again, you can check if you take the derivative of this, right, I'd bring down the 4, I'd get 12x squared. Good, right, and the constant would disappear. So this is the first derivative. which means that the original function y would be the antiderivative of this expression. Right? I want to take another step up the ladder. So again, I sort of take the antiderivative of this, 1/4 x to the fourth. And this is a constant, and so if I take the antiderivative of a constant, you just slap an x on it, right? And then I'm also going to get a new constant, right? My second constant of integration. So I can, of course, clean this up a little bit and get x to the fourth plus c1x plus c2. And this is my original equation, except it's got these two constants of integration here. So it's common to use different letters as well, like C and D, for example. I'm just using subscripts. But the point is you need these to be different, so somehow distinguishable from each other. And now I'm going to go back and use my initial conditions to figure out exactly what these were. So I know that when I plug in 0, I'm supposed to get 1, and when I plug in 3, I'm supposed to get 8. So in general, if you have the data point that goes with 0, that's the one I would use first. So y of 0 is 1, as you can see, our first initial condition. So y of 0, that's 0 to the fourth plus c1 times 0 plus c2 is supposed to be equal to 1, right? Well, this is a 0, this is a 0, so that just tells me immediately that c2 is equal to 1. Okay, great. So now I know that y is equal to x to the fourth plus c1x plus 1, right? Because here this c2 now I know is a 1. And now I'm going to use my other initial condition, which was that when I plug in 3, I'm supposed to get 8, right? So I do y of 3, that is 3 to the fourth plus c1 times 3 plus 1, that's supposed to be 8. So this is just a linear equation with one unknown, right? So 3 to the fourth, that's 81, 3c1 plus 1 equals 8, right? And then I'm just going to solve this for c1, right? So 3c1 plus 82 equals 8, 3c1 equals negative 74. So c1 equals negative 74 over 3. And then you can check, is this divisible by 3? Turns out it's not in this case. So here is c1, which means that my original function y is x to the fourth minus 74 thirds x plus 1. Right, because I recovered c1, that was my coefficient on x. Right, c1 is my coefficient on x, and at this step I recovered that c2 was equal to just a single 1. So after I've recovered both my constants of integration, now I know that this was the original function. And it's straightforward enough to check that if you take two derivatives, you end up with the thing you're supposed to get. But there are plenty of other functions, right, that would have a different coefficients on x and the constant whose second derivative would still give you the 12x squared that we were supposed to start with, right? So you really have to work in these initial conditions and make sure that your math sort of checks out, because if you're trying to recover a specific antiderivative, then you can't just rely on the check of taking the derivative at the end and making sure you started out with the right function. So this is sort of baby chain rule, taking antiderivatives when the interior is a linear function, and then also incorporating boundary conditions or so-called initial conditions.